Okay, well, it's my great pleasure. I am acting today as the substitute host because our normal host is giving the talk today. This is Ramani Duraiswami. Very pleased to introduce my next door neighbor. Ramani is the director of our perceptual interfaces and reality lab. He does work in all aspects of high performance scientific computing, machine learning, particularly with an interest in, perceptual, sound and whatever, audition, and has numerous patents, has 2 spin-off companies when the software is used in many of the, audio devices that we have. And all of this doesn't explain the most important element of Ramani's achievements, which is he's the only person I know who can hit a tennis forehand both left-handed and right-handed. So very distinctive.
Thank you. Yeah, I'm also proud of that. Yeah. So let's get to the talk. So we are sort of in this age where everything is being sort of reconsidered because of the start of a genuine cusp in the progress of human science and history, which is the evolution of Gen AI. And how we can bring Gen AI into audio is a topic that has sort of occupied me over the last 3 years. Yeah.
What is Gen AI?
Generative AI. So basically, you ask a model a question. We'll sort of look at examples. You ask a model a question about something, about an image, about audio or something, and the model answers and solves the problem that you asked it about that image or that audio piece or whatever.
That's the definition?
No, the definition is the model generates contents based upon your prompting. So it could be a piece of language, it could be that's where it started, but here our goal is to have it just like, I asked my intelligent student a question about something, and he's an expert on music, and he answers that question, and he generates an answer from whatever he is trained in the thing. And I want the same thing to be done by a model. So let's get this going. So, of course, audio as a modality. Yeah.
What is general?
General intelligence. So one of the goals or one of the fears that people have is that AI is going to come and become a general intelligence, which is going to essentially replace humanity's intelligence and do the things humans do. And as far as sound is concerned, it is not yet at that stage. Our goal is how do we bring these models to that stage as far as sound is concerned.
That stage is the human?
As good as the best human, the top 90% of human working in that domain.
So when we say general,
yeah,
we mean human?
Human, yes. That's the only intelligence we know so far. We do know some animal intelligences, yeah.
There could be something above.
Yeah, there could be, but it sort of remains to be. So audio, animals are particularly good at perceiving audio. Their survival depends on it. And here are 3 sort of examples of animals that do an incredible job. The barn owl in pitch darkness can find a mouse under hay and catch it. A bat can emit sound and from the reflections can sort of avoid tree branches and also catch insects. A dolphin in the ocean can do various things. Of course, in these animals, there is no language, and we'll come back to that in a second. But as far as humans are concerned, we use audio not only for sort of situational awareness like these animals or avoiding predators, we also use it for communication. Speech forms the basis of language. Verbal and non-verbal sounds allow rich communication, and listening to music evokes sort of deep feelings of pleasure. So I teach a course on computational audition. The next version of that course will be in spring. And we deal with a whole bunch of classical problems, which essentially involve either capturing sound, processing it, converting it from a physical to a digital representation. We discuss speech recognition and so on. And all of these problems have decades of work, which might not involve AI at all, right? And in general, the attack on these problems followed the scientific method. We have experiments and hypotheses, we have physical models, and perhaps we have computational simulations based on those physical models. Over the last 2 decades, and you can sort of imagine that this model is physics or math based, and you have some way of prescribing some inputs X and getting some outputs Y. On the other hand, over the last 2 decades, what has happened is, oh, this thing came back again. How do I get rid of, hold on. I guess I'll move this to the side, yeah. Yep. So over the last 2 decades, there's been sort of another approach which has become popular, which is learning from the data. And here we have some sort of a model. It might be a regular machine learning model, might be a statistical machine learning model. And this model might have some parameters theta that you specify based upon a whole bunch of data that you see. And these models might not come from physics, or they might incorporate physics at some low level. Our goal still is that the model should generalize and be explainable. And these are more driven by trying to minimize some sort of an error. And this has happened over the last 2 decades, I would say. And especially with the coming of deep networks, these models became really popular over the last decade or so. So over the last 3 years, foundational models have arrived. So these classical models were based upon signal processing approaches and simple statistics. Deep learning with sort of convolutional networks allowed us to extend the use of data. More recently, in my group, we have been looking at a couple of approaches like differentiable modeling and implicit neural representations to find latent structure in the data. And I'll be talking about this work on differentiable models and implicit neural representations in another seminar in the applied math department. But this talk is going to be about something that's actually become only prevalent in the last 3 years, which is generative AI. So this is scary. It seems to be all-knowing. It's already revolutionizing our professional lives, summarizes our email, writes our presentations for us, or at least you think it does, and then you have to do it, come in at 5 a.m. and actually do it. Or you know, it's sort of helping you code Maybe professors are going to be replaced, and there is another meeting going on today on education and how AI is going to affect it. This talk is how do we make Gen AI understand sound? How do we make it solve the problems, that large list of problems that I listed earlier on? And how do we assess how good are the solutions that Gen AI produces? Someone wants to enter? Yeah. So this thing, I guess. So to begin with, how did Gen AI come about? Gen AI essentially uses large language models. Large language models were revolutionized by this one paper in 2017 by Vaswani et al., where they introduced a new architecture called the transformer. So how do these transformer-based large language models work? You feed it text. The text is embedded in a d-dimensional vector space as tokens. It's fed into this architecture called the transformer architecture, which has multiple layers. Each layer has an attention mechanism which finds relationships between the tokens. And then there is a sort of a nonlinear projection of the output of this attention mechanism into the next layer using a multi-layer perceptron. And these models are essentially trained on all the data the person can get, whoever is training it, the company, the person, whoever else. And current models are trained on trillions of tokens and have billions of parameters that need to be figured out. Training these takes months, costs millions of dollars, and consumes hundreds of megawatts of energy. So these are essentially crazy new artifacts, which is like nothing you have encountered before. It's a new way of doing learning, which people like me or you who are sort of older, this is not within our paradigm of how learning should be done. All these things do is predict what the next most probable token of language should be. But these things have absorbed the whole world's knowledge. How do you use them? So you make them usable by doing something called post-training. And in post-training, what you do is you have a collection of another set of data where you take not trillions of pieces of data, but only thousands of pieces of data, which you then sort of structure in the way a human might answer a question. And you adjust the weights of the model slightly to using algorithms called supervised fine-tuning or various versions of that, LoRa or reinforcement learning or whatever else. And now you have a usable model. So the first such successful model was GPT-3. And GPT-3 was trained on 500 billion tokens. Google also had such models, but it didn't have this next piece, which was the chat. And GPT-3 was then trained with this thing called instruct GPT. So if GPT was trained on this much data, the instruct GPT was trained on this little data, a few thousands. And this post-training is also called alignment, and there are a whole bunch of algorithms which are used to do post-training. And applications in chat, coding, and other domains sort of are now highly prevalent and very highly successful. And their extension into audio, vision, and video is sort of what's going on. It's already also pretty successful, but it is sort of improving. Please go.
Before you go further, as you were saying, the basic model is predicting the next most likely token.
Yeah.
You've got thousands and thousands of tokens.
Yeah.
And it's calculating
Trillion.
millions of tokens. And it's calculating probabilities.
Yeah.
So the most likely versus the next most likely, how far apart are those probabilities?
They could be, it depends on the question you ask and so on. It could be quite extremely close or extremely far. So what happens is in the inference stage of these models where you actually ask, you pose a query and you sort of ask you pass sort of relevant data context, and then in this stage, those probabilities are changed according to the query. And this alignment phase, what that does is it gives the model for that specific subdomain what sort of answers you're looking for. It sort of further skews the probabilities in the direction that you want.
So all these computations of probabilities and weights and all that are treated as real numbers?
Yeah, they are real numbers.
Precision, triple precision?
They are actually, that's a whole bunch of other subjects, but people started with using, regular sort of floating point arithmetic for these, but now because these models get larger and larger, they're experimenting with even 16-bit, 8-bit, 4-bit, and even 1-bit versions of these models. So this pre-training part, using this transformer architecture, is extremely robust. In fact, this transformer model seems to have infinite inductive capability. You can feed it with more compute and the test loss goes down. You can keep increasing the data set size and the test loss keep going down. You can increase the size of the model and the test loss keeps going down. So in some sense, these models have already scraped all the data that is digital in the world and have learned everything that is possible to learn in some way. And in some sense, it's like an idiot savant went into a library and read every book there was, never smelt a flower, never sort of saw an animal in the forest, never heard a piece of music, but knows everything there is to be known about these things. And the goal of post-training is to get this idiot savant to help you to actually solve real problems in some way. So this post-training is brittle. Even though these scaling laws are incredibly good for the pre-training part, post-training algorithms, how they work is less understood. They require very little data in comparison to pre-training. And post-training, the model after post-training is sort of can suffer from various things such as hallucination, catastrophic forgetting, mode collapse, etc. And this part is still an empirical science. And I still would like to use that analogy that you're talking to this idiot savant friend who may or may not know exactly what is to know about that real domain, and you might ask them the wrong question and they go off and give you an answer from the wrong textbook, because that is what these sort of failure modes actually become. So you think it's a Superman, but actually it's this person here. But anyway, that's just and in some way I showed this to my daughter, and she said that I was being very I had implicit biases hidden in this picture, but that's sort of a separate yeah. So now let's go to this actual problem that we are going to be looking at, which is how do we use large language models with audio. And I would like to, in particular, in these things, old professors like me, when we actually want to go into a new area, the way we go into a new area is to find great students who pull us into that area. And I, in particular, want to thank Shreyan and Sonal and the others for having pulled me into this area. Over the last 3 years. I mean, this field only appeared in the last 3 years, and we have sort of already, moving forward in this. Yeah. So our goal is to build large audio language models. So what are audio language models? So they take a trained large language model, and they fine-tune that large language model with audio examples. So what you try to do is you try to move the audio itself into that same latent space, the token space that the language model learned. And you try to create a shared latent space between the audio and the language modalities. And there are a whole bunch of mechanisms that people have tried. So for example, you might have a piece of sound which is paddling in the water. And you also have the sound of someone actually paddling in the water. And you take the text in, you take the audio in, and then you try to align the two representations so that they match up. And the first such model to do it was called CLAP. It was contrastive learning on audio pairs. So it sort of learned this shared representation using audio and text pairs. So CLIP was the first such model. It came out of OpenAI, and it learned this for images and text. CLAP came out of Microsoft. It learned such a sort of alignment between audio and text. And this was useful for tasks such as classification, audio text retrieval, and text to audio retrieval, and audio captioning, and so forth. So our first contributions came in trying to improve the quality of CLAP. Which we did by sort of figuring out time alignment issues, adding time alignment into CLAP. But then came the next phase, which is you take an LLM and you try to integrate the audio in using one of these shared representations. And we had a whole sequence of papers coming out of our group, including Gamma, Audio Flamingo 2, Audio Flamingo 3, and just released, being released today, Music Flamingo. So all of these are capable of captioning, reasoning, and open-ended question answer on audio. So at a very basic level, what are we doing? We have text, which is a question or an instruction. We have audio, which could be speech, music, sound, or noise, or some combination thereof. The audio might also include instructions for the model. These are fed in together into this large audio language model. This model has been fine-tuned to answer questions about the audio, and it spits out a text answer. Newer versions of our models and others' models also spit out audio as an answer, but the simplest version of these models spit out some text as the answer. And these models have general capabilities that allow them to answer questions about the input audio. And in fact, they have what's called emergent abilities. And Yanis, before you ask me, I'll say what emergent abilities are. So emergent abilities are things that you did not give the model during training. So essentially, if you trained a human on music, and after a while, when they learned the music, they would have an emergent ability that they would be able to understand new pieces of music or synthesize new pieces of music based upon the knowledge they already carried in their brain, even though they might not have encountered that in their training data set. So these models have these emergent abilities as well. Yeah. So the language model and the audio come together to form an audio language model. So here the words are not, it's not a single token audio language, but they're separate audio and language. So this is a large language model fine-tuned with audio over a common representation of audio. Yeah.
Is the knowledge the knowledge that is captured in the relationships between the text? Or for example, there is knowledge in the sound waves themselves. If I ask, what is the timbre? What is the frequency? Or does it sound like something?
That is captured, but mostly currently through a path through the text. So this is this, it's like that guy went to the library, learned everything about timbre, etc. in the text, and then you passed the tokens which mapped the audio to those tokens, and then they went to that previous knowledge that they had, swatted up. Yeah. That had the trillion tokens of learning, and this has only the thousands of alignment things which are happening.
Audio extension.
Yeah, of the large language models. Yeah, yeah.
I mean, the model like Shazam program has
Yeah.
been around for a long time that can detect the songs and such things.
So those are mostly working on metadata. So they are, so for example, you might be the best singer in the world, but if you sing that same song, it will not recognize it. All it does is it builds a hash of the actual song that you learned, and it's of that piece of commercial music, and it matches that hash level. Whereas, in fact, the model Music Flamingo we'll show today could actually be used for the kind of thing you Shazam in the wild kind of a thing. Mm-hmm. Yeah. So I'm going to this field is kind of crazy. Every month or every 2 weeks, there's a new paper. If you have an idea and if you don't jump on it right away, there are 10 teams in China and 3 in the US and 1 in India or Europe, which is already working on that same idea, and they will scoop you. So you better jump on it and move. And is this good science? Some people tell me it's not. Some people tell me, this is the new normal. So let's go with it. Anyway, so let's not discuss that and let's move forward. So these models keep coming out. In the past, there used to be an area of research which was how do you figure out how good these models are. And if you ever did a DARPA challenge or whatever else, you would have benchmarking. But now, what has happened is there are essentially one sort of side of this industry of developing models is developing models. The other side is building benchmarks. And for audio models, there wasn't a comprehensive benchmark until our team built one. So this is called MMAU. It's sort of it's similar to MMLU, which was a language benchmark, which was highly influential. And we released this benchmark towards the end of November last year, or middle of November last year. And it was published at ICLR this year. And we essentially curated a whole bunch of questions on speech, music, and sound, and asked these of the various models that had been developed. All the questions were, sort of, there are groups of people talking, who spoke first, who appears to be the boss, how does it do the tongue twister, you play music, you sort of ask what kind of music, there's a scene, you ask what kind of scene, etc. And the skills, somehow, oh, what happened here? Yeah, so the skills we had was speech, sound, and music. We had things like harmony and chord progressions, event recognition, knowledge retrieval, musical texture, and we had things like, did the emotion of the speaker change? Were they happy at the beginning, sad at the end? If 5 people are talking and one of them has a bad emotion, what's happening? How do you interpret ambient sounds, etc.? And what kind of musical instrument is playing, and so forth. And here are some benchmark examples. So you sort of have a drum music play, identify the total number of drum beats in the audio, what might have caused the dog's reaction, not the Sherlock Holmes question, but which is why the dog didn't bark. We don't ask that. No, that's so which speaker's emotion changed, and so forth. And in early 2025, the best models actually did very poorly on our benchmark. They were about 50–55% at most. And this was Gemini Pro, which is Google's model, which is trained on lots and lots of Google data. So this essentially allowed people who are working on these audio language models to figure out where they should focus their attention, where they should focus their training, and so forth. So there was, and then we also started developing our own audio language model, Audio Flamingo 3. This was done in collaboration with NVIDIA, where Shreyan was also interning. And this model is available on Hugging Face. You can upload your own audio and ask it questions, and you can get answers on that audio. The code is completely open. You can download it. In fact, there are many groups which are using this audio for this model for various things all around the world. And Lasha actually put it on Hugging Face, and that's one of the good contributions. And this model was trained on millions of audio pairs. So it sort of, It also does chat, and it also does something called multi-turn reasoning. So you can ask it follow-on questions about the same piece of audio to make it reason through that audio. It's based around a different kind of encoder called the whisper encoder, which is very common in speech, but we extended that whisper encoder not from speech to other kinds of sound and music as well. The training was sort of a curriculum training. We can go into those details, but I want to keep this talk high level. Essentially, this model, even though it's it's open source, it beats most of the other models. And this pesky little thing always keeps coming up and that's the orange thing, the previous state of the art, which is open source, and the previous closed source. We beat them in on most existing benchmarks. So here are sort of, you like to find check boxes and you want to check everything of yours. So otherwise you don't show this. But anyway, we are better than these other models, which are in all these other things. So let me play an audio demo. So let's see how that goes. So.
Oh, I must be in the wrong class.
Oh, no, you're in the right place.
Did I get the time wrong?
No, it's just you and me.
So the question is, how many students are there in the class? And choose the correct option. And our model actually reasons through it and gets the answer. The speaker mentions just you and me. The presence of a teacher and the sound of a door suggest a classroom setting. So the most plausible answer is 1. Other models cannot sort of handle that. So here is another piece of, what happened here? Anyway, that audio somehow didn't make it, but this is a melancholy piece of music, and these other models don't understand it, but our model says, man is driving, singing a sad song, nothing really matters to himself along with the radio. Anyway. So I mentioned we had this benchmark, and everyone was, about 40, 50 when we released the benchmark. But by the time from November 24 to July 25, when we released Audio Flamingo 3, everyone started cheating on the test, and they all started reaching 80 and 90% performance on the test. So this sort of showed that benchmarking is an arms race. You need to create more robust benchmarks. You need to hide the question paper so that the students don't make a question bank and train on that question bank. So that sort of took us to the next project that we had. And we did this summer. It's called MMAU Pro. So I was leading a workshop in the Czech Republic called the JSOLT workshop. And I had the good fortune to work with 25 people. And you can see all their names here. It's I think this is the paper which has the most number of co-authors and that I've been on. And we created we didn't use any databases to source our benchmark. We sort of collected audio from the wild. So this is all the categories of our benchmark: spatial audio, multicultural music, voice QA, long audio. Previous benchmarks stopped at 30 seconds. So this went up to 10 minutes. We had mixes of speech and sound, and so on. And we also looked at giving instructions to the model using the audio, as opposed to giving the instructions in the text. And these skills were mapped in various things, and this paper has had very good reviews in AAAI, so hopefully it'll get in. And it also covers perceptual skills, and we also maintain a leaderboard. So humans are at 78% on this benchmark, and the leading models are still at most 60%. They haven't yet reached this, but of course, like I said, it's an arms race, and we'll eventually get there. So the next thing was, where do the models do the worst? And we found out the models do the worst on music understanding. So over the last 2 months, since during the JSORT workshop and since then, we have been training a model for doing music understanding. So in particular, data is crucial. And there is this sort of crazy school teacher in Germany who collects data, and all the image models are actually based on his work. He has a foundation, non-profit foundation called Lion, and he collected image text pairs, and that trained Stable Diffusion and all these other things. That's when what's his name? When the guy from Berkeley came, he was using this guy's data, etc. And now he's put his attention on emotion and music. And we trained our model on this. So I sort of jumped to my, hold on a second, to my, I wanted to show that slide as the last slide. So let me just go ahead. So we collected a whole bunch of data. So data is the new oil, as they say. We collected a whole bunch of data, and these kinds of data sets with many millions and so on. And we trained this, we fine-tuned Audio Flamingo further. And eventually we got this Music Flamingo paper out, which we've just submitted. It's going to be released today. It does a great job of doing sort of lyrics transcription, and it sort of, it reasons on music. It's got a complex annotation pipeline. We have keys, chords, beats, lyrics. We have music captions of the segments. We combine them into an LLM. We have reasoning chains and question-answer pairs. And then in the training pipeline, we use something which was new in audio, which was reinforcement learning, and Lasha worked on that. And we got basically a model which is sort of at the top of the game. So it beats all the other models on music QA and reasoning, music information retrieval, and lyrics transcription. So I think I'm 5 minutes away. So I wanted to do a real demo. I think I have time to do it. But before I go to the real demo, what I'll do is sort of I'll end with quotes from things two of our famous alumni are doing. On the left is Sergey Brin, who got his only degree at UMD in computer science. And he went back to work at Google Brain. And he said, it's no fun being the 5th richest person in the world if you're a computer scientist. It's a unique time in history. Anyone who's a computer scientist should not be retired right now. They should be working on AI. There's never been a greater problem and opportunity, a greater cusp of technology. And the building we are in is named after this guy, Brendan Iribe. And he did this Oculus startup, which was acquired by Meta. Now he's working on another startup, which is essentially building smart glasses which understand the audio in the environment you're in and captions it according to whatever data you want. So now let me stop the share and switch to the demo. And if Lasha, it doesn't work, I will rely on you to make it work, but hold on a second. So, too many windows. So here we go. So before I came in, I fed it Taylor Swift's most recent song, something about Ophelia. I forget what the thing. And I asked it to ask this model to describe the song from both a technical and artistic lens. Our model was trained before Taylor's model dropped. Taylor's song dropped, not model. So it's called The Fate of Ophelia. And it says, I asked the model, describe this song from both a technical and artistic lens, mention tempo, harmony, and instrumentation, but also mood, lyrical themes, and structure. It says it's a synth pop, electropop piece that blends bright dance floor synth textures with polished pop sensibility. It moves at 125 beats per minute in a 4/4 time and is rooted in F major, giving the music a consistently uplifting tonal center. I couldn't tell you if that's true or false, but that's what the model says. It's built upon layered synthesizers, arpeggiated leads, lush pads, and a punchy synth bass that drive the harmonic rhythm. Electronic drums provide tight side chain compressed kicks and crisp snares, and so on and so on. And the vocal characteristics, a female lead delivers clear melodic lines with a slightly breathy timbre. Her performance is expressive and confident, enhanced by tasteful reverb and so forth. And this demo thing will also be potentially out soon, but since we are in an anonymous phase of our review, we can't yet release the demo page yet. But thank you, and we have a couple of minutes for questions. That we haven't trained for that. That would require a data set to train with notes and so forth. But that is certainly something to consider.
And do you do any pre-processing in terms of sort of the plasticity of the sound if you talk slower or faster or higher pitch?
No. Yeah.
Both ways were limited by not doing the foundational model from scratch.
So
I realize the limits.
yeah. So the big limit is the size of the models. So this model had to learn the entire library, and we didn't know where it learned, and a certain brittleness in the model. So the hope is if you have a foundational model, the model will be less brittle. And we are actually working towards foundational models. So I did have one slide which I didn't show, which is sort of the open problems slide. Let me, or where did it go? So the open problems slide is, I think, the last. Yeah, so not open, current problems. So right now we want to also output audio. So we want a unified representation both for inputs and outputs. And foundational models that are audio and acoustics first is something. So you have to somehow do a self-supervised. Those models are likely to be much smaller. But on the other hand, the kinds of questions that you ask them are going to be, you have to figure out how to ask them the correct kind of questions, because language is an extremely convenient method of asking questions. Hanan.
I have a question. First of all, I've been working on things like unsupervised learning for news articles and things like that. Are there, most of the work you spoke of was referring to supervised?
No, the basic model is unsupervised. It learns its structure inherently inside using this next token. Only the part which is supervised is the post-training, where you sort of tell it, these are the kind of questions I'm going to ask you, kind of.
Isn't that sort of like when you do that post phase, you're sort of leading the device or the computer, the person, whatever it is, to the conclusions that you want?
Not exactly. You are sort of giving them the general area, but yes, you are. There is one of the sort of evaluation things that we have to be always careful about is, does it just parrot the answer in the which was there in what you trained, and we have to protect against that, and we do.
I have a couple more. How far along is the group, is the meta object on the eye? I ask because when Google Glass came out, that was the time when but nothing was done in that.
Yeah, so there, it was ahead of its time. So the deep learning was there, but what hadn't yet come out are these large language models, and which, like I said, absorb the whole library. Now it's a new time for these, because now they can go to the back end, which can actually answer general free-form text questions.
Has Meta made any progress?
Significant progress. Significant progress. Very significant progress. And also Sesame, which is Brendan's company, has also made significant progress. They have also released 2 large audio language models, which sort of, they just raised a $250 million from some VCs.
One other question about when you said inputting all the books. I think a judge has imposed on ChatGPT to pay $3,000 to every author.
Let's not get into the legalese, but
No, I don't mean legally.
yeah.
I'm just saying, is that part of the?
So there is a lot of material which is not in copyright. There's a lot of books which are there, and then there is also this notion of fair use. And many, in some ways, I would argue that there might be a fair use exception. But on the other hand, I might argue that because that advances my research, so I'm biased. But on the other hand, if you wrote a book and and ChatGPT sucked it all in, then you might not be so happy. But I did write one book, And in 2 years, I found it on a Russian website. So I don't care much for that.
One point of interest, your former student, Yanni Wexler,
Yeah.
was working on Google Glass.
No, he works now on a startup which does for the blind. Yeah,
Exactly, that's what
yeah,
we had talked about.
yeah. Okay.
I have a more of a foundational
Not these foundationals.
actually, this audio processing.
Yeah.
I mean, all the systems that understand audio in the biological world.
So, in the biological world, audio comes much earlier, the language is much higher. You need to, we need our foundational models to go to such a sort of model as opposed to go language first and then go down. Of course, and we need it all to be regulated by the various systems, have different reward models, different according to the time of the day, according to your endocrine secretions, whatever else. Sorry.
Yeah, so fundamentally,
Yeah.
all these things that you described,
Yeah.
okay, if you take away the, the paraphernalia,
Yeah.
they amount to multimodal representation.
Yes.
But if you look at the evolution of mammals and humans, language came last.
Yes. 100%.
So that means that we developed multimodal representations without language.
100%. Yeah.
And I believe this is a fundamental question.
Yeah. This is the fundamental question, which are foundational models that are audio and acoustics first, and only then go to language, maybe as a way to query those models or whatever else. They will be much smaller, much tighter. And the other important thing is they'll be less prone to hallucination. So one point is, sound in the real world is associated with physical events or people, or actions. Yeah,
And that brings me to my second question.
yeah.
In this whole audio analysis that you gave, where does the activity of the agent come in? Because every system that understands sound is active.
Yes, this is all in our this part in future work. But Yanis, what I want to tell you and people who have been working, with old important ideas, is that this is a new beast. It is not something which was there before, and we should think about how to use it in all our domains, using the knowledge that we have.
Absolutely. And we have a unique opportunity, I believe, within UMI to create the next layer of AI, which is basically integration.
Yes.
We have to integrate all the different modalities, as opposed to expecting to have one piece of software.
No, and it's a much smaller problem. The possibility of all vision things, the possibility of all audio things, the possibility of all haptic things, all motions, all actions is infinite. But when you put them all together, they live in a very, very small subset, and the learning will become easier.
Exactly.
Yeah.
Okay, we're pretty much out of time.
Yeah.
So we should maybe take remaining questions off.